When working with real-world problems or word problems in two variables, you use a lot of the same strategies you use with one variable equations. When you're reading the problem, underline and write down key information so that you can translate those words into an equation, and make sure you understand what the question is asking for. But with two variable equations, it's really cool because what you're talking about is you can change the value of one variable and it will then change the value of the other variable. And you can look at those situations in different ways with an equation, a table, or a graph. And what you want to be able to do is to create all of those things so you can understand what's going on. Let's look at an example. For a school dance, you have a budget of $40 for balloons and flower arrangements. Each balloon costs $2 and each flower arrangement costs $4. Write an equation to represent your situation. So notice how while I'm reading this, I'm using the strategies over here of underlining key information to try to make sense of this problem. So what they want is an equation here. And we realize here, let's see, each balloon costs $2. So if I take the 2 and I multiply it by the number of balloons, and let's just go ahead and use B for balloons. And each flower arrangement costs $4. So if I add how much we're going to spend on flowers, that would be 4, and let's use F. So you can see that what we've done here is we've taken $2 for each balloon, so 2 times the number of balloons, plus $4 for each flower arrangement times the number of flower arrangements. This is the total amount that you're going to spend. And we know that that has to be less than your budget of $40. So we can say that that equals $40 if you spend everything that you've got. Okay, now we've taken the first step here of writing an equation. Now let's look at the next step. Your class president says she wants 4 flower arrangements. How many balloons can you buy? Okay, well what we can do is we can take that 4 and we can just put it in here for the F, because that will be the number of flower arrangements. So let's go ahead and do that over here. So 2B plus 4 times 4, that's the number of flower arrangements, equals 40. And then we can go ahead and solve. So that would be 2B plus 16 equals 40. Then we know that 2B, when we subtract 16 from both sides, will be 24. And then that means that B will equal 12 when we divide both sides by 2. So what you can see here is that we have a relationship between the number of balloons and the number of flower arrangements. If the number of flower arrangements is 4, then the balloons must be 12. Now let's take a look at another step. Okay, your class president changes her mind and wants 5 flower arrangements now. So we can do the same thing we did before. 2B plus 4 times 5 this time equals 40. And then that will be 2B plus 20 equals 40. And 2B equals 20. And so B would equal 10. So that's our answer this time. But we're getting a little bit worried here because what if our class president keeps changing her mind? This is a lot of math to do in order to find out how many balloons you can get each time the class president changes her mind about the number of flower arrangements she wants. And so what you can do is, if you anticipate that your class president is going to keep changing her mind, you can put the equation into a different form. In other words, you can calculate B based on F. What do I mean by that? Okay, well let's look at the original equation up here. 2B plus 4F equals 40. What if we subtracted 4F from both sides? What would that look like? So then we would have 2B equals negative 4F plus 40. And then we could divide both sides by 2 so we get B by itself. And then you have B equals negative 2F plus 20. Now, each time your president changes her mind, you can just plug this number, the number she says, in for F here, And then you can quickly calculate b without doing as much math as you had to do here and over here. And that is really where these equations really get powerful, is when you put one variable in terms of the other variable. You've solved for one variable, and then you can quickly calculate its value based on the other variable. And let's look what this means so here you've been putting together equations. Let's look now at tables and graphs and how powerful those can be. So here I've taken our equation, and I've also set up a table where we can put values in for the equation. And this is a way that you can avoid being surprised by all the changing of the mind from your class president. You can just put a whole bunch of values into this table, and anytime your class president says, oh, I want this many flowers, then you can say, okay, well then you can afford this many balloons. So let's put just a few of the values in here. For instance, if we say we're going to have 0 flower arrangements, then if you put 0 in for F up here, well, negative 2 times 0 is just 0, so B will just equal the 20. So we can go ahead and write that into our table. Now what if we just wanted 1 flower arrangement? Well, 1 flower arrangement here would make this term negative 2. Negative 2 plus 20 would just be negative 18. So we can put those values in here. 118. Go ahead and get that right. Okay, now what if we wanted 3 flower arrangements? Well, 3 times negative 2 would be negative 6. Negative 6 plus 20 would be 14. So we can go ahead and put that value in here too. 3 and 14. And you could go on and on putting more values into the table. And then you could just read from the table anytime your class president changed her mind. Now there's an even better way, and that's to make a graph. Let's take a look at that. So the table is great because it has a lot of values, but it doesn't have every possible value. A graph, though, can have every possible value for you. So here we've made a graph of the values in the table. So here we had 0, 20. Well, here's the point 0, 20. And here the point 118. Here's the point 118. Now what does this mean exactly? Well, you take the input value, which is the first variable in your table, and you put that on the x-axis. And then the output, the other variable, you put that onto the y-axis. And you could, if you want, label this axis F and this one B, but usually we just leave them as x and y when you're graphing. And so here you can put in all of the combinations that were on your table, plus every single combination in between. If it was possible to have 1.5 flower arrangements and just half of a balloon, it might be in between here. That's not possible in this case, but this line kind of shows you all the possible values that you could potentially have. And then when your president says, you know what, I changed my mind again, I want 8 flower arrangements. Well, you can go over here and find, let's see, 5, 6, 7, 8, and go right up here, and you can see that at 8 flower arrangements, there would be 4 balloons that you could afford. And you can read those values, any possible values, off of the graph. So that's why we always try to, in addition to creating an equation, we always try to think about tables of values and also graphs. And with 2 variable equations, that becomes really powerful for solving real-world problems like your class president changing her mind.